Welcome. In this little tutorial, I'm going to show you how to build a language in MPS. We'll build a little state machine language with events, variables, states, transitions, and guard conditions by reusing an existing expression language. We'll also build a second language that tests the original state machine language, and we can even run this to execute the tests. Finally, we conclude by illustrating how to build tabular notations and diagrams as part of the overall state machine story.
All right, so now let's integrate KernelF expressions as guard conditions into the state machine. So the point is that one of these guard conditions should have one of these transitions should have a guard condition. So let's go here. First thing we're going to do is we're going to create a new concept, which we call the guard, right? And our transition has a guard optionally, guard 0 to 1. And the editor for the guard, how should it look? Well, basically, the usual convention is that a guard condition is enclosed in square brackets, right? So here is and then here goes the expression, right? So we'll get to that in a moment. So then this means the transition, before the arrow, I want to put a guard. So the thing is, if we do it this way, then every transition, even if there isn't a guard, it has this empty placeholder, right? That's ugly, so we can add a guard, then it looks like this. Of course, we'll replace that thing here with the actual expression in a moment, but this empty thing here is ugly. What is much nicer is to say, okay, please show this guard thing here only if there is actually a guard. So in other words, the empty placeholder goes away. So show this only if the guard is not null. So now, of course, the notation goes back to here, but now I can't even enter a guard because there is no placeholder. So what do I do? Well, one thing that you could do is you could define an intention, right? An intention is basically you call the intention add guard for the transition. You give it as a, the string in the menu would be add guard. You have this intention only if your transition's guard is null, so if it doesn't already have one. And then what should happen if the intention executes? Well, you said guard.set a new one, create a new object and set it there. And now you can grab this intention, press Alt Enter, add guard, and it adds the guard. So that's fine, but the problem is now you have to use the kind of intention style. You can't do it with just typing. So long story short, what you really want to do is you want to do this slightly differently here. You want to use a grammar.optional. Grammar is something you grab from the grammar cells. You remember at the very beginning of this tutorial we had a grammar flag. We used that for the initial flag of the state. And now we put the guard here. And so basically the grammar optional can be, or by default shows nothing, but it still allows you to enter something. So how do you do that? Well, you register a transformation text. So what does this mean? Well, it means that if you are here in this place and you type this transformation text, then it creates the object, in this case of type guard, and you can delete it again, and it's not, there's no empty placeholder. So it now behaves basically like a text editor, which is exactly what you want. Right, so that was the guard object, which we can now insert into a transition. Now we want to, in the guard, of course, have an actual expression here. So it's pretty clear that there needs to be kind of a child called condition, which is an expression. Now expression is that thing we grab from KernelF. But we don't see it because my state machine language has no dependency on KernelF. So let's change that. Let's open the properties, the preferences of the language, and create a language dependency on IATS3 expr.base. So the KernelF language actually resides in IATS3 core expr, right? That will change at some point to actually, use the word KernelF. So we create this dependency, and now we're able to use the expression here, okay? And it's exactly 1, right? The guard itself is optional, but then the expression in the guard is mandatory. And so we replace this with the actual condition, and then we do a little bit of editor magic, punctuation right and punctuation left to remove the white space between the brackets and the condition, and recompile. And now, unfortunately, there is no transitive import, so we have to go to this model property here and also use expr base, and we'll in a moment need expr simple types. You can do that a bit more elegantly by using a dev kit, but for now I don't want to bother with introducing the notion of a dev kit. Dev kit is basically a collection of languages which you can then import in one step. I'm reloading the classes here just to make sure that everything's up to date. And so now I should be able to add one of these guards, and so I should be able to write 12 plus 12, which is, if you remember, an expression from KernelF, where you can do something like this. So that's fine, except that this is not valid because, of course, the type here is a number, but the condition must be Boolean. So what we need to do next is we have to integrate a type system rule, which basically says that for a guard, right, one of these guys here, right, we need a type system rule that says that the type of the guard's condition must be Boolean. Now, normally we could just simply say, we create a Boolean type object here, which isn't visible right now because we have to include the structure model that actually includes Boolean type, and we want the one from IATS3 expressions. So now we have a Boolean type. So this is a type equation. MPS's type system is based on equations and a solver in the background, and basically this says for the type system to be in a valid state, the type of the guard condition must evaluate to something that is the same as what's on the right side. On the right side is a kind of in place created instance of the concept Boolean type. So this is only correct if the type of the guard condition is a Boolean type. So let's see. Going back here, I have to press F5 once to recompute the type system. Normally it does it incrementally, but if you change the typing rules, you have to kind of push it by pressing F5. And now you have an error because number 24 and Boolean is not compatible. If you change this to that, then it's fine. I mean, it's still kind of pointless, but from a type perspective, this is now correct because the greater than operator, of course, is type Boolean. So that's good. Now, what really is missing is the ability to refer to variables, and also the variables aren't there yet. So let's create something which is the var_decal. It's also something that has a valid name. I also express the fact that it optionally has a type. So, well, let's not do that for now. I'll do that in the next step. So, so the variable only has a name and it has an init expression, right? So an init value, which is also an expression, and that's right now. For now, that's exactly 1. And so now, how does the editor look? Well, var, name equals, and then the expression, okay? And now to make the variable plug-inable into the state machine, we just implement iStateMachine content. Remember, this was the interface that was used as the children of the state machine. So now we can go back here and put a var counter equals 0, right? Or 0 plus 1 times 2, right? I can put any expression here, and that's fine. Now, what's the type of that variable? Right now there is no type, right? It doesn't have a type because we didn't tell the system how to define the type. So let's go back to the variable declaration and define another one of these type system rules for the var bar, right? Whatever, name doesn't matter here. So the type of the variable is, for now, the type of the variable's value, right? So we use type inference. We take the variable, the value of the init expression and propagate that to the type of the variable. So because the type of 0 is of course a number from 0 to 0 with 0 decimals, the type of the whole variable is now also 0. Now you might want to also explicitly specify the type, and to do that we can do this slightly differently. We can implement optionally typed, that is an interface that also comes from KernelF, and it brings a type child where I can optionally specify a type explicitly. So how would I do that? I would go to my variable declaration and I would say here is something that is optional, which is a horizontal list that is a colon and then the optional type object, right? So if I do that, I can now go back here and I can say colon, and now I can select any of the types that KernelF comes with. For example, I can say this is a number type between 0 and 100. What's the problem here? Yeah, so now we have a problem because the optionally typed thing comes with a type system rule that says if on that node a type is specified, then the type of the whole optionally typed is the type that's given here, right? So let's check this out. It says if the specified type is not null, then the type of the whole thing is the type that's explicitly given. Now, of course, this conflicts with the type system rule we wrote explicitly, because here we say that the type of the variable must be exactly the type of the value. And the type of a value is, of course, number 0, and this one is number 0 to 100. So that's wrong. What actually is needed is that the type of the init expression must be the same or a subtype of the type that's explicitly given if one is given. And so that is also already coded in the optionally typed, which is basically discussed here. But to make that work, we have to implement a method that tells the framework which node it is from which we derive the type if it's not explicitly given. So in other words, we have to implement a behavior method here in our variable declaration and return the node from which the type should be inferred. Inferred if no explicit one is given. And of course, that is the value, right? The init value that we've given. And now we can also delete our explicitly created typing rule because the optionally typed does that for us. So rebuild. And now pressing F5 once, that's fine, because number 0 is a subtype, because a subrange, of this one. I can put 200 here and I get an error, because number 2000 is not a subtype. I can put a string here and of course it's wrong. I can put 50 here and that's fine, right? I can put string here and now that's wrong. I can concatenate that like this and it's fine, because that's an implicit to-string type conversion. So this is now really quite fancy. It's a optionally typed variable with type inference and compatibility checking, and it's all done basically just by implementing this interface, because it comes with its typing rules that does that. So how does it do it? Well, it basically says if an explicit type is given, then the type of the whole thing is always the explicitly given one. And then if there is a node from which we derive the type. Then, if no explicit type is given, then the derived type wins. And if a type is given, then, well, this one has already executed, but then the type that's specified must be the same or a super type of the type of the value that's given as the init parameter. And so that's the behavior you expect, and it does exactly what you think it does. So, all right, we can now declare variables here. Cool. Now, next up, we need to be able to refer to that variable here. How do we do that? Well, we said that everything here must be an expression, right? If we look at the greater expression and go up to its binary expression, general one, then of course the left and right argument are also expressions. And so what do we have to do? Well, we have to create basically an adapter, an expression that connects the expression world to its environment. So basically, we create the variable ref, which is an expression, and it's a smart reference, so its only purpose in life is to be an expression and refer to a variable. So the variable is the var decl concept that we created before, exactly one, and the editor for the guy is the variable's name. And we need a scoping rule because we have to define which variable declarations are visible, and it's very simple. We just go from wherever we are, context node, we go up the tree until we find a state machine, grab its contents, and check if, and from those we filter. We want to have only the variable declarations, and then of course we have to again wrap this into a list scope. List scope. We've done that before, if I remember correctly, for named elements like this. So now I can remove the 12 and, for example, use counter. Counter is now our var ref, which refers to the variable. It finds that variable because from here it goes up the tree to the state machine, grabs all the contents that are actually variables. Cool. Only problem left, it doesn't have a type, right? So it complains it can't compute the type, and then therefore this one doesn't really have a type, and okay, it uses a different type system rule to somehow make that Boolean, but this is still broken. So what do we have to do? Well, what is the type of a variable reference? Well, the type of a reference is almost always the type of whatever the reference references, in this case the variable. So we just propagate the type of the variable blah 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 to the variable reference. Rebuild. Press F5 once to retrigger the type system, and now we get an error here because this is still a string, so let's change that back to number, remove this, and now everything's fine because this is now also a number because that's declared here. If we remove this, then of course the whole thing is a number from 50 to 50, and therefore this is a number from 50 to 50. So, and that is of course, we could perhaps statically know that this is always true, but we're not that sophisticated. All right, so we've integrated expressions syntactically, we've made them nicely editable. You can just type it as if it were a text editor, and type checking works, and we have variables with optional types, and it's all very little effort because you get all this infrastructure from KernelF. In the next iteration, we're going to look at how to build an interpreter that actually runs this.